Good afternoon. Welcome to today's HydroCAD webinar. My name is Peter Smart. I'm the developer of HydroCAD, and I'll be presenting the session this afternoon. Today we're going to be discussing the modeling of low-impact development elements within HydroCAD. Basically, these are techniques which are used to reduce the impact of development on a site. Roughly, the topics we're going to be covering is, first of all, why do we need LID techniques? Why is this becoming more important now than it has in the past? Then we're going to talk about some of the common LID elements that you might include in your site. They might include infiltration effects, whether you're introducing it with porous pavement, dry wells, underground storage, or other techniques. We'll also talk a little bit about bioretention or rain gardens, and some about how you can measure pollutant effects, both pollutant loads and pollutant removal. And of course we'll be talking about how some of these elements are modeled within HydroCAD. Most of the LID techniques, as you'll see, are modeled using the fairly traditional runoff and routing capabilities that are in HydroCAD and other models, but they are often applied a little bit differently to LID scenarios. Okay, let's take a step back and just talk first about the issue of why we need LID techniques. Why is this coming into play? And it helps, I think, to step back and look at the basic runoff issues that are being affected when we develop a site. In an existing condition, if we had, for example, a curve number of 65 for woods in good condition, and if we evaluate the SCS runoff equation, it will tell us that 3 inches of rainfall produces approximately half an inch of runoff from those woods. If we take that same area and we were to develop that entire area and bump the curve number from 65 up to 98, then that 3 inches of rainfall now produces 2.8 inches of runoff. So we have more than a 5-fold increase in the volume of runoff coming off that same area in a developed condition. And this really illustrates just how dramatic the effects of development can be. One of the most common approaches to mitigating that increased flow is to construct detention ponds, and this is what we've been doing for some decades now. And what we do with a detention pond is simply to detain the water. We hold it in a volume and release it more slowly. And by doing that, by releasing it over a longer period of time, we're able to reduce the peak flow. So we achieve the basic goal of trying to take our developed peak flow and reduce it to some target level, and your regulations will determine that. Often you are allowed to only discharge your pre-developed rate, or perhaps 90% of that or 110% of that. It will vary depending on your regulations. So detention ponds have been a common approach to dealing with this. But the difficulty with detention ponds is that we are not reducing the volume in any way. So when we reduce this peak flow, we are creating a broader peak. So the full volume that is created in the developed scenario is still there. The pond itself has not mitigated that effect. It has knocked the peak down. So we're fine as far as immediate effects near the site, culverts, ditches, and so forth. Although we have a much longer duration of flow, so we have more erosion effects and other problems. The next thing that happens to us with peak widening, and here's our volume, by the way. This is when you do build a detention pond, the area between those two curves is essentially the volume that we are going to be detaining. Now, we do need to have a careful look at what happens to detention ponds in terms of the larger watershed. If this slide illustrates 2 existing sites, one in blue and then a second in green, showing here a hypothetical offset flow. So here's site 1 and here's site 2. When we combine those 2 sites, we get this final red curve. And you'll notice the offset peaks mean that those peak flows do not add directly. In fact, the combined peak of these sites may only be a little bit larger than their individual peak flows. That is quite common. Now, the difficulty comes if we develop site number 1 here and build a detention pond in order to maintain the same peak flow in the proposed condition, but then we combine it with other flows in the watershed, that combined flow can be considerably higher than it was in the pre-development case. So this illustrates that simply managing peak flows at the site boundary is not sufficient to ensure that we're not having effects on other people downstream. And this is what's generally happening in most developing regions in very much of the country. We're developing and using local peak flow type regulations, but this is causing peak widening everywhere, and so we get more and more flooding that's happening further downstream. And I believe that we see this from a very large scale up to very large river systems. They're all suffering from this same effect of peak widening, because we're not really dealing with the volumes. That's the key issue. We're just dealing with peak flow. And so what we're talking about in many cases with low impact development is actually techniques to try to manage that volume and not just the peak. We're looking at techniques for distributing the mitigation measures throughout the site. Rather than just using centralized detention, we are now trying to infiltrate water as much as we can, either to prevent it from running off initially or infiltrate it through other measures within the site. And there are, as you know, a lot of different techniques that are coming into play for this kind of more elaborate management. Rain gardens and bioretention are certainly an example of one of those approaches. We'll talk about that today amongst a number of other different capabilities. All of the topics that I'm going to cover today do have specific articles on our website, and we'll be glancing at some of those pages today, but you can find those later. If you go to hydrocad.net and click on support, you'll find these and other resources listed on the support page. Porous pavement is obviously another evolving and emerging capability for low impact development, and we'll be talking about a number of different techniques that you can use for modeling porous pavement on your site. So that is a brief introduction to why we need LID and some of the kinds of techniques that we might be dealing with. Let's have a look first of all at, I should also mention, we're also going to be talking a bit about pollutant loads. Removing pollutants is the qualitative aspect of low impact development, and we'll be looking at techniques for evaluating pollutant loads and removing pollutants within a site. To give you just a quick look at the pollutant loading calculations, this is a capability that's in HydroCAD. You may not have seen it, but if you open either one of your existing projects or this sample project that's pre-installed with HydroCAD, and if you come over to the icon on the right-hand side here, the little house, this is where the land use settings exist. And if we come over here and click that, then we can turn on a land use reporting capability, but in this instance we also want pollutant loading. And when we select the loading, we have a number of different options here for exactly how the imperviousness will be calculated for the purpose of this loading calculation. If you click the Help button, as always, it will give you detailed information on each of those options and on exactly how the land use or the loading calculation is being performed. The second tab on the screen allows us to define the specific land uses that will be used within this project, and then the columns at the top allow us to specify the pollutants. In this case, we've got total suspended solids, phosphorus, and nitrogen, and then we can specify the concentrations of each of those pollutants for each land use. So this lets us set up the specific pollutant concentrations that are required by our local regulations. When we click OK on that screen, if we now look at any of the subcatchment summaries within that project, we have additional information that's now shown on the summary. We have the basic land use that's reported in this column up the top, and then we have a new table down the bottom which indicates that we're doing a pollutant loading calculation, in this instance for 42 inches of rainfall, so this is presumably a total annual pollutant load, and that this particular subcatchment is 3.2% or actually project level imperviousness is being used here of 3.27%, and this calculates, it gives us a runoff coefficient and calculates the total loading in pounds in this particular report for each of our pollutants for that subcatchment. So that all happens on a subcatchment basis. If we now open the project report window up on our toolbar, we can come over to reports that show us our land usage analysis for the project. So this shows us how many acres we have in each land use. We also have a table that reports all of the pollutant concentrations that we have defined, and then we can look at the subcatchment loading. So here we have the loading for each subcatchment showing the total weight of each pollutant within the project. And we can also get a breakdown by land use on a project-wide basis. So here we see the load that we get for each land usage. There are a number of different techniques for calculating the imperviousness, and that's one of the things you'll want to look at in the HELP system. You'll need to study your regulations specifically to see how you want to use that. The simple method is one of the techniques that's available, which calculates the loading based on imperviousness, but you also have the option to calculate the pollutant loading on an individual event basis, to have HydroCAD use the actual rainfall that is being calculated, such as with the SCS method, and use that to do your loading. So you have those and other options available to you. So this is just to let you know that those loading calculations are available to you in HydroCAD. At the moment, there is no pollutant removal capability in the software. That's something we're hoping to add in a future release, and that will allow you to specify the percentage removal, for example, for a pond or a treatment swale for each of the pollutants. And based on that, it will be able to propagate those total reduced pollutant loads down through your system. So that's something we're looking at for the future. But just being able to get the loading calculation saves you a lot of work as compared to having to do this parallel analysis typically in a spreadsheet outside HydroCAD. The next thing related to pollutant loading I want to talk about is the detention time. When you open any report window for a pond, if you go to the summary, one of the elements of the pond is a detention time, and you find that information right here in the report. And there are two detention time values that are being reported. The first of these is the plug flow detention time. Plug flow detention time, as its name suggests, uses small plugs of water in order to determine how long the water is resident in the pond. And in this instance, it's estimating 105 minutes of detention time. There's also a center of mass method, and that value is also evaluated here, and it gives us a similar value of 98. The two procedures will normally give you fairly close values as long as your pond meets a relative textbook case. That is, it starts dry and all the water empties out of the pond. In other scenarios, you will find that the center of mass method may not give you good predictors of the detention time. And in those cases, the plug flow method will often give you a better result because it's looking at a more detailed physical view of each plug of water entering and leaving the pond. The center of mass method, as the name suggests, is just taking the center of mass between the inflow and outflow hydrographs and measuring the time in between them. So it is a relatively simple visual process. In comparison, the plug flow method is taking the inflow and dividing it into a large number of plugs of equal volume, calculating the time span between each pair of plugs, and then averaging all of those times together. So this will work with a wet pond, which may have existing water in it, and it's based on a first in, first out scenario such that all the water in the pond will be displaced before the new inflow discharges. So that wet volume will increase your detention time, whereas if you were running center of mass method on that, the wet volume would not affect the detention time. So there are some differences you need to understand, particularly when you start to see a deviation between those two sets of numbers. So this is information's here. This is one of the techniques that you're looking at to evaluate perhaps pollutant removals. Sediment removal time would be your detention time. And often your regulations will have some specific numbers as to the amount of detention time that you need to provide. The next capabilities I want to talk about are subsurface detention, retention, and infiltration. I started by talking about traditional detention ponds, which traditionally just detain the water. They retain the entire volume, and so the entire amount ends up being discharged from your site. There are, however, a number of techniques you can use to combine infiltration with your storage effects. And one approach to that would be to use a dry well. And a dry well could simply be a circular excavation which has been lined with block, or it could be a prefabricated leaching catch basin or something of that nature. In any case, what you're going to do is you're going to create a pond to model that structure. And on the storage tab, you're going to define the storage. In this case, I'm using a vertical cone or cylinder. So I've simply got a 20-foot diameter area. It's 20 feet high, quite large. Of course, you probably aren't going to have a dry well this size, but it does illustrate that you need fairly large volume in order to deal with the typical runoff. Small dry wells that you might put under a downspout at home don't do very much for you when you're dealing with larger site modification changes. So the fairly large volume is provided in this example. We could also have storage provided perhaps in the stone around this leaching dry well. That would be another possibility. To do that, we would define the overall volume that's being filled with stone, set its voids to perhaps 40%, and then we could take our actual dry well structure and we could embed that inside the stone, leaving that at 100% voids. In this instance, I've just got that inner dry well, so I'm assuming that we're not taking credit for any additional storage that we might have in the stone that surrounds the dry well. So we have a vertical cone and cylinder for modeling the dry well, and then we need outlet devices of some kind. Actually, we don't. We could just have a complete retention structure if we want to size it to hold the entire volume. And if you have to reduce your flow to zero, then that may be what you need to do. In this instance, however, I've added two outflow elements. One of them is exfiltration. So we are going to allow for water to infiltrate into the soil around the dry well. And if we edit that outlet device, what I've specified here is a constant exfiltration velocity. So we're simply setting a velocity of 3 inches per hour, and we're specifying that that velocity will be applied against the entire wetted area. By picking wetted area, we're specifying that it will infiltrate through the bottom of the structure as well as out through the sides of the structure. So all of the areas that are wetted will be subject to the same 3 inches per hour of exfiltration. Then I've also specified an overflow device in here. I've got a culvert which I've placed up 16 feet from the bottom, and this will just handle the overflow that might occur in larger events. So those are our two outlet devices and our storage definition. And if we click OK and then double-click this pond in order to open up a report window, we now get the routing results. You'll notice that at the moment in this model we have just a 2-year event selected. So we have no blue outflow. The blue is our primary, which in this instance is our culvert overflow. So the water is not getting up as high as the culvert. We are getting some exfiltration flow. We're getting 0.06 CFS. And we can manipulate this view, such as changing to a 2D and switching it to full screen and even zooming in order to get a closer look at what's going on in that graph. There it is zoomed in a 3D view. So we have our inflow in green, the brown is our exfiltration, the blue is our overflow, no overflow, and then the gray is the combination. That's the total of the exfiltration and the culvert overflow. Now, as we increase our storm event, for example, if we change this to 50-year, now we do start to get some overflow. in blue. So we are filling the dry well up to our overflow device. So we're starting to get some discharge. You'll notice we also have a warning message which has appeared down the bottom here. Do keep an eye on these warning messages, particularly the red warnings, because they're conditions that you need to understand and preferably resolve. In this case, if we click this message, it's telling us that the early inflow requires an earlier time span. So if we look carefully at the hydrograph, what's happening in this case is that we have some runoff that's occurring before 9 hours. If you zoom right in here, you can see there's actually that little bit of flow at the 9-hour mark. So there's some inflow happening before 9 hours. And in order to fully include that volume in the model, we need to adjust our time span. So we might bring that time span back to 6 hours, for example. And now you can see that that warning message has been resolved, because we essentially have zero flow that's at the 6-hour mark. So we started early enough that the entire volume is being captured. So that's a basic dry well example with an overflow. That's one of the kind of techniques you might use. And it's actually a pretty similar approach that you would use for rain gardens or most other situations where you're combining infiltration and detention in order to maintain the water flow or minimize the discharge from your site. If you look at the summary, we can see exactly what's going on here. We have a total inflow volume of 0.33 acre feet, and to make that a little easier to understand, if we go to Edit and then the Storage tab, actually what I want to do is to go to the project level. If we go to Settings Units at the project level, you'll find a box labeled Use Large Units for Areas of Volumes. If we uncheck that, then our project level reporting will be in square feet and cubic feet as opposed to acres and acre feet. And so when you're looking at LID techniques and relatively small areas, the numbers will often be easier to comprehend. So now you can see that our total inflow volume, which is our runoff, is about 14,000 cubic feet. Of that, we're infiltrating, that is the discarded flow, about 8,000 cubic feet, and about 5,000 cubic feet is overflowing. So this is the actual volume reduction that we've been able to achieve for a 50-year event by inserting this dry well into the system. So we're reducing the peak flow from 5.2 to 3.34. That is what the overflow peak rate. But we're also reducing the volume at the same time. So that's the kind of general goal we're seeking with most of these LID techniques. The other tabs in this report window are always worth reviewing. We looked at the hydrograph. A useful tip there is to right-click the hydrograph, go to Report Items, and select the elevation curve. And this will show you what the water level is doing in that dry well over time. So you can see how we're filling the dry well basically up to the overflow, and then it's staying there for quite a period of time and gradually dropping. So that's very useful in understanding the outflow nature of your structure. The discharge curve shows us the stage discharge relationship for exfiltration. And what you can see is we have a relatively small amount of exfiltration over here, just a fraction of a CFS at the left axis, versus our culvert. The culvert does not discharge anything until we get up to 116 feet, and then we get a fairly rapid increase in flow as we start to get water above the inlet of the culvert. And of course we have the storage tab, which gives us a simple linear increase in storage for this particular storage definition. There is also a sizing tab. The sizing tab is very useful when you're designing ponds. It allows you to estimate the amount of storage you need in order to reduce the current flow you're getting into the pond to a given target level. So for example, if our target level were 2 CFS, then we'd come across to the curve and down to the bottom axis, and it would tell us that we need approximately 4,000 cubic feet of storage in order to reduce this specific inflow that we have to this pond to a given target level. Remember that the sizing report is just an initial estimating tool. Your actual design and your final analysis is going to be based on the simulation of the pond with its storage and outlet parameters. This sizing report does not directly affect your final results. It's really just an auxiliary report. Other techniques you can use for underground storage and infiltration would be underground chambers. In this instance, what we have set up is a series of perforated corrugated metal pipe, which has been placed in a stone bed. In this instance, the field has been set up with the chamber wizard. The wizard makes it very easy to lay out that field. And the wizard automatically creates the storage definitions for the outer stone field and the embedded chambers. And if we edit that storage, it takes us to the wizard screen where we're able to select, for example, we could change this from 30-inch to a 24-inch pipe, and we could click the Use Typical Spacing box in order to respace the pipes for the new size, and that recalculates the entire field layout and the corresponding storage. And click OK a couple of times, and now we're back to our modified report. So an underground chamber system is another technique you can use. This system is similar to the dry well in that we have exfiltration, which we are applying over surface area in this case, and that's discarded because that's a loss, that's a volume being exfiltrated into the soil. But we also have an overflow culvert, which we've placed a couple of feet up above the bottom of the bed. And then the table up top is showing us our corrugated metal pipe embedded inside our outer field. And again, we can come up and we can look at our results. We can see we have an inflow volume of about 14,000, and we're actually exfiltrating about 11,000 of it here, and just about 4,000 is overflowing. So this analysis will help you to see the actual volume reduction that's occurring. And then so there are a number of different techniques you can use for storage and infiltration. They're all similar in that they're going to have an exfiltration outlet, and then you're probably going to have an overflow device of some type. The next thing I want to talk about, here we're dealing with collecting the water and then providing a pervious surface or an infiltration capability. But if we back up a level, the next thing we can try to do is to actually reduce the runoff that occurs in the first place. And this is often attempted with porous surfaces, porous pavement, porous concrete, porous pavers. There are a number of different products that can be used to do that. And so we reduce the amount of water that comes off those surfaces. We have less that we need to handle in a pond. It reduces the need to build underground structures to do the infiltration. One of the common techniques that's being used and discussed a lot is porous pavement. There are a number of different techniques for modeling porous pavement, and this is really something that you're going to need to discuss with your reviewer and decide how they would like you to handle the pavement. One of the things that you need to keep in mind is that LID techniques are usually designed to handle low volume, low intensity rainfall events, partly because that's when most of your pollutant occurs. I believe, depending on your location, more than 90% of your pollution is occurring running off your site in events that are less than an inch of rainfall. And so providing techniques that can handle those low volumes is very useful. However, those same systems, once you put a 10-year event on them of 3 or 4 inches, may just be overwhelmed. So the presence of these LID elements in your HydroCAD model is something you need to think about and work out exactly what the goal of your model is. If you're setting up your HydroCAD model primarily for peak flow management, then you may find that many of these LID techniques have a minimal effect on what's happening during that 10 or 25-year storm. You may also find that your local ordinances don't want to allow for the porous pavement in the management of the 25-year and longer event. They may want to be sure that they're dealing with a worst-case scenario where that pavement may be frozen or otherwise plugged, poorly maintained, whatever it might be. So although they may want the porous pavement there for water quality improvement and management. They may also be requiring you to manage the peak flows, even with that pavement in poor condition. So you're going to have to discuss with them the best approach to implementing this. The different options that you have in HydroCAD when you're actually modeling the pavement, sort of three different cases. One case would be the situation where the pavement is able to intercept and absorb all of the rainfall that's falling on that pavement. The UNH Stormwater Center and other labs have done a lot of testing on porous pavement, and I'd certainly urge you to look at their studies. Some of them are quite impressive as far as how much water can be absorbed through the pavement. In most of these systems, of course, the total volume that a porous pavement system can handle is heavily dependent on the base that's under the pavement. The paving layer itself has a relatively small volume in the voids. The voids are really being provided by the layer that's underneath. And in the UNH case, they actually have a test system they've set up and a design they've evolved which involves a base of approximately 41 inches of sand underneath the pavement. And this provides a delayed detention effect to let the water slowly seep through that layer. And they've modeled that successfully by using a time of concentration of approximately 800 minutes for that pavement. So what they're doing is using a CN of 100 typically. So we have to flip the model around a bit. We're no longer talking about water running off. Instead, we're using our subcatchment to capture the rainfall that's falling on the surface of this pavement. We want to intercept all of that rainfall in this situation, hence a curve number of, of 98 or 100. But then, as it goes through the pavement, it immediately hits this sand layer that takes it quite a long time to penetrate through the layer. Then underneath the sand layer, we are also usually have a bed of stone. So we have this total section of stone, sand, and pavement. And the stone underneath provides an additional longer-term storage for detaining that flow. And it may be that that is able to gradually exfiltrate into the surrounding soil, or we may have a case where we can't rely on subsurface infiltration, and instead we're putting in outlet pipes, such as a perforated pipe, which you could model as a culvert outlet at the appropriate point. So that's a common setup if we're allowed to assume that there's no surface runoff, that we're absorbing everything through the pavement. And switching back to our HydroCAD model, here's a pavement scenario, these two nodes. And what we have is we have our pavement modeled with a very short TC. So we've got a curve number of 98, and we've got an arbitrary TC of 5 minutes. You could actually set that TC right down to 0 in order to get instantaneous runoff, because what we're looking at here is that the water hits the pavement and is immediately being absorbed. So there's really no delay. So in this situation, we're letting the water go right through, and we're actually just bringing it through into a stone base. So there's no intermediate sand layer in this scenario. So if we look at the routing through this system, our stone base is being modeled. I believe we have, I've set up a custom areas. So we have 0.4 acres, we have 1 acre overall that's been provided. And we have 40% voids in that space, so that's providing 0.4 acre-feet of storage. So the water is going rapidly through the pavement into this lower layer of stone. And then we have an exfiltration outlet, which is allowing the water to infiltrate from the stone into the surrounding soil. And so in this instance, we're essentially exfiltrating our entire volume. We have no overflow device. And if we have a look at the numbers here, our storage starts at 100 feet, and our peak elevation is 100.31. So we're just getting 0.3 of a foot of water of depth in this storage. Basically, we're providing enough stone to retain the entire rainfall event, is what it comes down to. So you can do this calculation very simply. You don't need a full hydrograph analysis. If you want to be able to detain 6-inch 100-year event, then you need to provide the equivalent of 6 inches of voids in your stone. So a foot of stone, for example, would give you about 4 inches of voids in that space. So 1.5 feet would give you enough capacity to completely retain that 6-inch event. And then you would still be discharging it perhaps through an underdrain or via infiltration, but the rate at which that occurred would not be a critical element of your design, because you'd be able to retain everything so you can allow it to infiltrate over a fairly long period of time. Now in this instance we've provided 1 inch per hour of exfiltration, and so we are able to infiltrate that fairly rapidly because we've got a very large area here. Our infiltration area is the same as our subcatchment area, because we have stone under the entire pavement in this scenario. And so we're seeing that infiltration. We're getting a flat top here because we have a constant infiltration area. So the infiltration rises and it's steady until the water empties out, and then the discharge just tracks our inflow after that. Again, you notice we're getting this warning about early inflow requiring an earlier time span, so we really should reduce that 6-hour starting point in order to get the earliest inflow coming into this model. So this is a scenario with pavement intercepting all the rainfall and going into a stone base. The next two nodes here are actually the UNH scenario, where instead of using a very short TC for the water going immediately into the underlying storage, we've specified a much longer TC. You can see here the value of 790 minutes. And again, we have a curve number of 98. You could use 100, indicating that the entire volume is going to be intercepted by the surface of the pavement. So this has reduced our peak flow, but remember, this is the flow that's emerging from the bottom of the sand layer. And so if we were to come back, we could actually compare these two. If we select these two nodes, this is our subcatchment with the short TC, this is the longer TC for the sand layer, and then if we select the comparison report on the toolbar, the message it's giving me here is because I have a second project open with a node selected, and it's actually able to compare any number of nodes across any number of projects. So we need to deselect that node, come back over here, and now with our two nodes selected, we can open the comparison report. So what we're looking at here is the two runoff hydrographs. This is the same area, but just a different TC. One is a TC of 5 minutes on the left here, giving us this 7.6 CFS, and then the TC of 790 minutes, which is knocking that flow right down. So that's the effect of the water flowing through the sand layer, and this is what they've determined by tests, that this is the effective hydrograph that they get, and it can be simulated by using that longer TC value. Now, once we've gone through that sand layer, we're still coming into a stone base. So we still have a storage layer underneath the sand, and again, we're using the 40% voids to allow for the storage in that area. And because the water's coming in here so slowly, it's able to infiltrate pretty much as soon as it comes in. So there's very little storage that's actually being used in that stone layer. Of course, if the infiltration rates were lower, if we went to our outlet and if we reduced that from 1 inch per hour to 0.1, then we do see some effect. Now the 0.35 CFS peak that is coming into the stone is greater than what we are able to infiltrate through the underlying soil below the stone. And so now we do have a longer time for that structure to empty. And we could go to our time span. We could increase that time span as needed. We could bump that up to 80 hours. And now you could see the entire hydrograph. And again, right-clicking and going to select our elevation curve, you can see the elevation curve that's occurring. So in this instance, it's actually taking a couple of days for that volume of water to infiltrate into that soil. So those are a couple of different options for porous pavement. this varies enormously depending on region of the country and specific regulations as to how the pavement is placed, as to what you use for base, and what the appropriate techniques are for modeling it. I would refer you to the article on our website that talks about these options for porous pavement, and that'll give you a little bit more guidance. But otherwise, you'll certainly need to talk to your reviewer and decide exactly what's appropriate from their standpoint. The next thing I want to talk about is artificial turf. Although this is not strictly considered an LID element, it's similar to some of the other things we've discussed in the way it's modeled. Artificial turf usually allows the water to penetrate very freely. It's an open mat, and it's usually placed on top of a sand or a sand and stone base in order to provide some storage. So in many ways, its behavior and its modeling is very much like porous pavement. And the design approach is often similar. That is, to provide enough voids in the base that we can detain the entire volume of our event and then allow it to either infiltrate more slowly or empty that water through an underdrain or an overflow of some kind. So our artificial turf would again be modeled with quite a high CN value. In this instance, we've got a CN of 98, and we also are using the minimum TC of actually 0 minutes. And HydroCAD will accept a TC of 0 minutes. When you do that, you get a warning message that we see down the bottom here, indicating that a TC of 0, or a hint, excuse me, TC of 0 causes instant flow, which is dependent on the DT. So there's no delay due to the TC. The unit hydrograph doesn't actually come into play. So our runoff is directly dependent upon our rainfall distribution and having a short enough TC. The shorter the TC, the higher the flow, because we're calculating that peak over a shorter and shorter time interval. However, the peak flow here is really not a critical factor because we are taking that flow and it is going through the turf and immediately into the porous base layer underneath. So we don't have any kind of piping or other system that actually sees that flow. The flow is distributed over the entire surface. So underneath the pavement, in this instance, we might just have a stone base, and what we've done here is we've set up, like the porous pavement, an area which is the same storage area as the area of the turf above. We've specified 40% voids, and then we've also applied an exfiltration. So this is how we're drawing down the water from the stone subbase into the surrounding soil over time. And again, the hydrograph will give us a good look at what's going on there. So this is another technique you can use, artificial turf behaving much like porous pavement, because the concept is that everything is being intercepted. You could have situations where this surrounding soil is impervious, and you could place under drains modeled as a culvert outlet in order to gradually drain that water over time. That's another approach that's available to you. Next, let's talk a little bit about rain gardens. Rain gardens are actually quite complex structures because you're dealing with multiple layers of material in a typical rain garden. You've usually got some kind of growth layer, and then you have filtration zones and also voids for storage. So there's a lot of different things going on within a rain garden. And then, of course, at the very surface, we have an above-grade detention or retention pond. Now, these layers take a large period of time, usually, for the water to infiltrate through the system. So again, we have to look at the analysis we're doing and make sure we're clear about whether we're modeling short-term peak flow effects or long-term water quality effects. It's not uncommon that you're going to need to look at these structures in two ways. You'll be building them so that you can handle perhaps a half-inch or a 1-inch water quality event. And in that scenario, you may want to have enough volume that you can actually retain that entire volume in the above-ground space, so that if you suddenly get that inch of rainfall, there's no time for it to infiltrate. You want to be able to capture all of that and leave it time to infiltrate through the layers below, which will take hours to days. Typical rain garden is not a rapid infiltration structure because you're trying to treat the water as it flows through. This means that for your larger events, your 10, 25, 50-year storm, you're going to fill the surface of the rain garden very rapidly. Most of your rainfall is occurring in just a very few hours, and so you're going to be dependent on overflow structures and above-ground storage of other types in order to manage the short-term effects. So this is to say that the detail of what's going on below grade, although it's critical to you for longer periods of a day or two as the structure dries out, it will have little to no effect on what's happening in the very few hours around your peak flow. So just keep that in mind as you're deciding how you're setting up your model and working out exactly which events you're intending to replicate in HydroCAD and what the objectives are in each case. Now, if you do go ahead and set up your rain garden in HydroCAD, what you're typically looking at is that you need to simplify the rain garden behavior in some manner. The pond mechanism that's available to you in HydroCAD is designed to model a level pool of water. So it's essentially an open volume or perhaps stone with voids. And the assumption is that the water is able to enter and forms a level water surface. That's what we mean by a level pool. The bottom of the pond doesn't have to be level. It's just the water surface. So all of the volumes are interconnected in such a way that the water equalizes quite readily and gives you this level water surface. And you'll notice, of course, that the rain garden has got a lot more complex stuff happening at the lower levels, that we're not necessarily just filled to some level with water. We have a pool of water perhaps at the surface, but then the material below may not be fully saturated. So the overall rain garden does not meet our definition for a pond. It is not just one pool of water. So in modeling it, we need to say, well, where is there a pool that we can treat as a traditional pond? And the answer to that usually is by looking at the above-ground storage, that it's this area above the media which is the pond that you're typically going to be simulating in your HydroCAD model. Then we may have infiltration representing the water that infiltrates through that layer into the layers of filtration and underdrain below. And typically the water coming through that underdrain is going to be significantly delayed. It might even hours to days after when the rainfall occurs. So the flow coming through there is not going to be occurring at the same time as your peak runoff that you're managing for the storm. So you need to look at the different issues. Having said this, people have modeled rain gardens as much more complex structures in HydroCAD by treating them as several stacked ponds. So you could set up a pond with 40% voids for a stone layer with a culvert outlet on it. Then you could have that fed by another pond, which is your above-grade storage and exfiltration that is going through the sand and into a second, quote, pond with the stone layers. So more complex setups are certainly available to you. In fact, the porous pavement UNH example that we discussed is similar to this in that we have a long TC for the travel time through a filtration layer, and then the water eventually enters a stone storage layer underneath. So this is to say there is no single way to handle rain gardens. They are inherently complex structures, and you're going to need to think about their behavior in deciding how you set them up in your model. I would urge you to have a look at this article on rain gardens on our website, and there are specific recommendations here, including some simplified scenarios. In this model that I've got set up here, I have set up this particular rain garden using a vertical cone or cylinder. I've got a one-to-one side slope here, so I basically got a conical, a truncated cone, part of an ice cream cone, which is providing our storage. And then we have a culvert, which is providing an overflow device. So when the water gets up 1.5 feet, then we will start to overflow through this culvert. And we've also provided exfiltration. So here we're modeling the exfiltration of water from the top growing layer of the rain garden down into the gravel underneath. And then we get final routing results for the structure, as we have in each of these previous models. We have the exfiltration in brown, relatively low rate, and then we have our overflow. This overflow is a culvert, but it could just as easily be a weir or some other structure. It could just be the berm at the side of that rain garden being modeled as a weir. Of course, rain gardens are usually fairly small. They're only designed to treat a relatively small area. But one of the approaches we're seeing is pavement areas being divided into smaller sections. Perhaps where we used to have a curb inlet for a storm system, we would now have a rain garden to collect the water off just that part of the pavement. So if you were trying to model this entire system, you might have a whole series of ponds, one for each rain garden, and you might have your impervious surfaces as a sequence of subcatchments along that. And so you just have a chain, which you can model by replicating these. So if we set up an initial subcatchment and pond, we could then do a controlled drag in order to create a second subcatchment. We could do the same for the pond. So now we have a second system, and then we could interconnect those two. So we might have another piping system that this water is flowing through, and we could take the overflows from each of these structures and we could run it into that pipe system. So various approaches depending on how your specific model is set up. So that is most of what I wanted to cover today. Check dams are also worth a mention. We get questions about those periodically. A check dam is basically a channel in which you're placing small broken rock dams, riprap, in order to detain the flow. Again, there is an article on our website that talks about modeling check dams. And the two basic approaches are to model the individual check dams as small ponds. So you could model the storage above each of those check dams. You would typically need to enter custom storage for this option. Although in some cases you might be able to use actually the box culvert option. Seems odd because it's open storage, but you could use a box culvert which allows you to set the slope. So that's one way that you could define a channel above that check dam. And then the check dam would need to appear as an outlet control, so that would be a weir, presumably, in your model. And you might even have seepage through the check dam, which is obviously more complex to calculate. Over time, that check dam is going to silt in, so you're going to have little or no flow flowing through the stone. But you might want to model the seepage perhaps as a special outlet device, perhaps by setting up exfiltration. There are a number of different options. You'll have to look at each individual situation. And then for your series of check dams, that would just be a series of ponds with one routed to the next. Now, another approach for check dams, because these are really very small volumes in each check dam, is that you might just use a larger Manning's value for the overall reach and do a reach routing in order to simulate the behavior. Do have a look at the Manning's value table, which is in the back of your HydroCAD owner's manual. That's got some high Manning's values for rough stone cuts and other such scenarios, so that might be useful to you. So you do need to look at what effect it has on the system and decide on the best approach to including it in your model. So that is basically the material I plan to cover today. One of the things you want to keep in mind as you're doing this is that HydroCAD is an event model, that we are dealing with a single event of a perhaps 24, 48-hour storm, something of that nature, or even shorter. And so we're dealing with the short-term flow effects. We're generally focused on peak management, whereas a lot of your LID elements are focused on very low volume events. It might be a 1-inch event or a 1-year event or something of that nature. So you need to make sure you're clear about the objectives of your model. Why are you setting up the model before you start throwing things into it? Because the manner in which you model these elements, or even if you include the element in the model at all, will depend on exactly what the objectives or how you set up the model in HydroCAD. Do go through all the HydroCAD reports, as I've urged you to do today. You can click on any of the items in these reports, particularly the pond summary, for additional information. You'll find lots of detail there. And do go to hydrocad.net and visit our support page, and you'll find all of these articles that I've been referring to today and others. And finally, if you do have any other questions, you can always contact us at support@hydrocad.net, and we'll be glad to get back to you. This session will be posted on our website. We're recording it. It will be posted on the site later today, so if you or others want to look at it, it will be available there. And we should have future topics for webinars posted on the schedule shortly. So I want to thank you all for joining us, and I hope we'll see you at a future session. Thanks very much, and have a great day.